The universe is a place of constant change. Stars explode, black holes devour matter, galaxies collide. Everything seems to have a beginning and an end. But what about light itself? Could the photons, the fundamental particles of light, be immortal? Photons are unique. They have no mass and travel at the speed of light. Because of this, they don't experience time as we do. A photon created billions of years ago is, from its perspective, just as young today. This leads to the fascinating possibility that photons could exist forever. The idea of eternal particles in a transient universe is captivating. It hints at a deeper order, a fundamental building block that persists through cosmic epochs. But is it true? To find out, we must journey into the realms of particle physics and cosmology. In the world of particles, stability is key. Some particles, like neutrons, decay quickly. Others, like protons and electrons, seem to last much longer. Photons, however, take stability to a whole new level. Photons are fundamentally different. They lack mass and always travel at the speed of light. These properties make them immune to the forces that cause other particles to decay. While protons might eventually break down, photons are theorized to remain unchanged. This stability is crucial for our universe. Without it, stars wouldn't shine and we wouldn't exist. Light carries information across vast cosmic distances. If photons decayed, the universe would be a much darker and less interesting place. The idea of eternal photons isn't just a cool concept. Several lines of evidence support it. These come from both fundamental physics and observations of the cosmos. One key piece of evidence is the conservation of electric charge. Photons have no electric charge. They can't decay into particles that do without violating this fundamental law. Einstein's theory of relativity also points to photon stability. Photons travel at the speed of light, meaning they don't experience time. From their perspective, decay is impossible because time doesn't pass. Finally, experiments haven't detected any sign of photon decay. Scientists have studied photons closely, looking for any hint of instability. So far, the results point to photons being truly eternal. While photons are incredibly stable, they're not completely immune to change. Under specific conditions, they can transform into other particles. These transformations, governed by quantum mechanics, showcase the dynamic nature of light. One example is pair production. A high-energy photon can interact with an atomic nucleus, transforming into an electron and a positron. This process demonstrates the interconnectedness of energy and matter, with photons acting as a bridge. In extreme environments like those near neutron stars, high-energy photons can collide and create particle-antiparticle pairs. This phenomenon, called light-by-light scattering, further illustrates the complex interactions photons can undergo. These transformations don't contradict photon stability. Instead, they reveal the amazing versatility of light. Photons can change form, interact with matter, and still retain their fundamental nature. The universe is expanding, and this expansion has a profound effect on light. As space stretches, the wavelengths of photons traveling through it also stretch. This phenomenon is known as cosmological redshift. Imagine a photon emitted by a distant galaxy billions of years ago. As it journeys towards us, the space it travels through expands. This stretches its wavelength, shifting it towards the red end of the electromagnetic spectrum. The amount of redshift is directly related to distance. The farther a galaxy, the more its light is redshifted. This effect is a cornerstone of cosmology. It provides evidence for the Big Bang and allows us to measure the distances to faraway objects. Section 6. A dance with matter photon. Absorption and reemission. Photons don't just travel through space uninterrupted. They constantly interact with matter, being absorbed and re-emitted in a continuous dance of energy exchange. When a photon encounters an atom, it can be absorbed. Its energy is temporarily transferred to the atom, exciting it to a higher energy level. However, this excited state is usually unstable. The atom quickly releases this extra energy by emitting a new photon. This re-emitted photon carries the same amount of energy as the original, but it might have a different direction, phase, or polarization. This interplay of absorption and re-emission is crucial for understanding how light interacts with its surroundings. It explains why we see colors and how light transfers energy within and between objects. Section 7. A tired alternative. Challenging the expanding universe. The idea of an expanding universe, supported by redshift observations, is widely accepted. This concept, first proposed by Edwin Hubble, revolutionized our understanding of the cosmos. However, alternative explanations exist that challenge this mainstream view. One such alternative is the tired light hypothesis. This theory was initially proposed by Fritz Zwicky in the 1920s as a potential explanation for the redshift of light from distant galaxies. This hypothesis suggests that photons lose energy as they travel vast distances, causing the observed redshift. According to this idea, the energy loss occurs gradually, leading to a shift towards the red end of the spectrum. Proponents of the tired light hypothesis argue that this energy loss happens through interactions with intergalactic dust or other unknown mechanisms. These interactions could potentially scatter the light, causing it to lose energy over time. However, the tired light hypothesis faces significant challenges. One major issue is that it fails to account for the clarity of distant galaxies. It fails to explain why distant galaxies appear just as sharp as nearby ones, which contradicts its prediction of light scattering. If tired light were correct, we would expect distant galaxies to appear blurred due to the scattering of light. Furthermore, it cannot account for the observed time dilation in the light curves of distant supernovae. Time dilation is a phenomenon where events appear to take longer when observed from a distance, a key prediction of the expanding universe model. This time dilation is a key prediction of the expanding universe model and is not explained by tired light. The expanding universe model predicts that as the universe expands, the light from distant objects will be stretched, causing time dilation. While intriguing, the tired light hypothesis lacks the observational support and consistency with other cosmological phenomena that have solidified the expanding universe as the prevailing model. The expanding universe model not only explains redshift and time dilation, but also aligns with other observations such as the cosmic microwave background radiation and the distribution of galaxies. Section 8. Particle or wave, the dual nature of light. The concept of the photon often sparks debate about the true nature of light. Is it a particle, a discrete packet of energy, or is it a wave, a disturbance propagating through a medium? The answer, intriguingly, is both. Light exhibits a wave-particle duality. In some experiments, it behaves like a wave, exhibiting diffraction and interference patterns. In others, it acts like a particle, carrying discrete amounts of energy and momentum. This dual nature is a fundamental aspect of quantum mechanics. It challenges our classical intuition about the world, where objects are either particles or waves, but not both. This duality also raises questions about the concept of photon stability. If photons are also waves, does their wave-like nature affect their lifespan? This question remains an active area of research in quantum optics and field theory. The journey to understanding light's dual nature began over a century ago with pioneers like Albert Einstein and Max Planck. Einstein's explanation of the photoelectric effect provided strong evidence for the particle nature of light. Meanwhile, the double-slit experiment vividly demonstrated light's wave-like properties. Today, scientists continue to explore this duality, using advanced technology to probe deeper into the mysteries of light. Understanding light's dual nature not only deepens our knowledge of the universe but also drives innovation in fields like quantum computing and communication. The implications of this research are vast, potentially revolutionizing technology and our understanding of reality itself. The dual nature of light remains one of the most fascinating and profound discoveries in modern science, continually inspiring new questions and explorations. Section 9. Beyond the photon. Implications for our understanding of the universe. The question of whether photons live forever might seem like an esoteric detail, something only physicists would ponder late at night. However, it has profound implications for our understanding of the universe and its evolution, affecting everything from the birth of stars to the fate of galaxies. If photons are truly eternal, they carry information from the earliest epochs of the universe, acting as time capsules that can reveal the secrets of the cosmos. Studying these ancient photons could unlock secrets about the Big Bang, providing insights into the very moment our universe came into existence. This knowledge extends to the formation of the first stars and galaxies, helping us understand how the universe transitioned from a hot, dense state to the complex structure we see today. It also touches on the fundamental laws of physics, potentially revealing new aspects of the forces that govern everything from the smallest particles to the largest cosmic structures. Furthermore, understanding photon stability is crucial for cosmology, the study of the universe's origin, evolution, and eventual fate. It underpins our models of the expanding universe, influencing theories about dark energy and the ultimate destiny of all cosmic matter. The cosmic microwave background radiation, the afterglow of the Big Bang, is a key area where photon stability plays a critical role. It also affects the evolution of large-scale structures, such as galaxy clusters, and the cosmic web, which are the building blocks of the universe. The pursuit of understanding photon stability drives us to explore the fundamental nature of light, matter, and the universe itself, pushing the boundaries of human knowledge. It's a testament to the power of scientific inquiry and our endless fascination with the cosmos, reminding us that every discovery brings us one step closer to comprehending the vast, mysterious universe we inhabit.
So hit that subscribe button, ring the bell for notifications, and let's turn the page on a new adventure together. Get ready to experience books like never before, only on VBook 360. Like, comment, and share to support the channel and keep the video magic alive. Thank you for stopping by. And remember, every video has a story, and every story deserves to be shared. See you in the next video.